This tutorial discusses the relationship between electrochemistry and free energy. Delta G for a redox reaction can be found by using the equation delta G is equal to negative NFE, where N is the number of moles of electrons transferred and F is the constant, the Faraday, which is 96,485 coulombs per mole. Under standard conditions then, notice that delta G naught is equal to negative NFE naught. Determine the delta G for the reaction I2 plus 2Br minus yields Br2 plus 2I minus. Alright, so to do this, we want to use both equations. In order to figure out what delta G is, we had to figure out what the cell potential is. Which means we need the cell potentials of the cathode and the cell energy of the anode. So we need to figure out which one's being oxidized and which one's being reduced. Notice that bromine is going from a -1 to a 0. It's losing electrons in this process. Lose electrons, oxidized. That means bromine is the one being oxidized. And its cell potential is positive 1.07. That means that I2, the iodine, must be the one being reduced, which is 0.54 volts. Altogether, that gives us I2 plus 2Br minus yields 2I minus plus Br2. We're going to do the cathode minus the anode, which gives us 0.54 minus 1.07, which gives us a negative cell potential. Alright, so now we're going to go back up and we're going to plug it into the delta G naught. Negative NFE, where N is the number of moles being transferred of electrons, F is the constant, and Ecell is the one we just calculated. So if we look up here, we're transferring 2 electrons. So it's going to be 2 times that constant times the voltage that we just calculated. Multiply that all together, and it comes out to be positive 1.1 times 10 to the 5th, or 110 kilojoules. Because delta G is positive, the reaction is not spontaneous in the forward direction under standard conditions. Alright, so let's relate this over to equilibrium. Remember, delta G is equal to delta G naught plus RT ln of Q. This means negative NFE, if we substitute in our equation for that, is equal to negative NFE naught plus RT ln Q. Dividing both sides by negative NF, we get the Nernst equation. Or, using base 10 logarithms, we get this equation. At room temperature, 298 Kelvin, 2.30 RT over F is equal to 0.0592 volts. Thus, the equation then becomes E is equal to E naught minus 0.0592 divided by N log of Q. Notice that in the Nernst equation implies that the cell could be created that has the same substance at both electrodes. So here we have nickel at both electrons, at both the cathode and the anode. For such a cell, the E naught would be 0, but the Q would not. Therefore, as long as the concentrations are different, the E will not be 0. A spontaneous reaction can happen when an oxidation and reduction reactions are the same, as long as the electrolyte concentrations are different. The difference in energy is due to the entropic difference in the solutions, because the more concentrated solution has a lower entropy than the less concentrated solution. So for here, 0.01 in comparison to 2.0. If they have the same concentration, if they're both 1, there is not a difference in energy between the two half reactions, and the Ecell is equal to 0. Notice when they're the same concentration, the voltage is 0. But when they have different concentrations, you have a voltage. In concentration electrochemical cells, electrons flow from the electrode to the less concentrated solution to the electrode of the more concentrated solution. The oxidation of the ions happens at the anode that is located in the half cell having a lower ion concentration, and it will increase the ion concentration of the solution. Reduction of the ions is the cathode electrode whose half cell has a more concentrated ion solution. So let's figure out one of these equations. We have copper going to copper 2 plus in a 0.01 molar solution, and manganate going to MnO2 in a 1.0 molar solution. So the E of the cell, the electric potential of the cell, is the standard potential minus 0.592 over N times the log of Q. The first thing that we're going to focus on is figuring out what the standard potential is. So we need to take the half reactions and balance them out. So here's copper, that's the oxidation, and here's the manganese, that's the reduction. We have 2 electrons here and 3 electrons here. We're going to try to balance it out. The smallest number that's divisible by both would be 6. So we're going to multiply the copper by 3 and the manganese by 2. Notice that when we did that, the cell potentials did not change. We kept them the same. It comes out to be 1.34. So here's the equation we just solved with 1.34 volts. Now we're going to plug it into the Nernst equation. We have 0.0592 divided by the number of moles. If we go back up here, we can see that the number of electrons that are being transferred is 2 times 3, which is equal to 6. That's where we get the 6 on the bottom. And then we do the products over the reactants. So we have copper on the right hand side on the products. So we need the concentration of copper, which is 0.01. That's where this number came from. And then the reactants. Solid we don't include. We have 2 aqueous concentrations. MnO4 is 2 molar and H plus is 1 molar. So that's how those are placed on the bottom. Now notice the little numbers. So copper 0.01, it has a coefficient of 3, so it's to the 3rd power. Manganese is 2.0, coefficient of 2, so it's to the 2nd power. And then hydrogen has a concentration of 1.0 with a coefficient of 8, so it's to the 8th power. That's where those numbers are coming from. Put all this math in, and you get negative 0.065 volts. Add that, you're minusing a negative, so it ends up adding to be 1.41 volts. And that's how you do the Nernst equation.